Hello there. Welcome to this presentation about FireBridge and what FireBridge is. And the purpose of FireBridge is to bridge the fire behavior analysts their predictions of fire intensity and rates of spread to the operations side to make it more conducive to match resources to predicted fire intensity. For the objectives that I have, never having done this before, is to understand what FireBridge is, to have one understand how to use FireBridge, know what a fire behavior nomogram is, understand the use of a fire behavior nomogram, know how to determine fire line intensity, know how to determine resource and types based upon the fire line intensity, determine thermal capacity of resources to more closely match predictive fire line intensity, and then to have a better appreciation for FBANs. So let's begin. So what is FireBridge? First of all, you have to understand that FireBridge is nothing more than a mathematical construct that allows one to bridge the gap between the fire side, which is what the FBANs are telling you is going on with your fire in terms of intensity and rate of spread and flame lengths, and the resource side, which is the operation side. That's where myself as a tender and dozer operator live, and the incident commanders, all of your division soups, task force leaders, strike team leaders, engine captains, etc., etc., and even the crew world and the hotshot world, they're all the operation side. So with that, let's kind of dig right in here. So you see down here, this equation right here, this is from Rothermel's 1972 INT-115 report, which was the first one to try to put a number to fire intensity and rate of spread. And so this here is the rate of spread equation out of many. And all it's saying is that the IPO, the no wind propagation intensity, which is your BTU per square foot, is multiplied by the wind coefficient and the slope coefficient, and then divided by the effective bulk density of the fuel, times the pre-ignition temperature of the fuel. Okay, and so down here I have it to where we have the bridge pillar on the fire side is really where your rate of spread, your heat per unit area, your intensity in BTU per second per foot, and then the heat generation in hundreds of thousands or millions of BTUs lives, okay? Then we'll have our water that we can use, but we can't bring it to bear on the fire effectively until we can construct our bridge. And this equation over here that I've worked on and developed takes into account the fire line intensity, which comes from this side. So you've got the intensity times the fire line length divided by the thermal capacity of water. That tells you the number of gallons, and then consequently from that it will tell you the resources and the types and the numbers to be successful. That is it in a nutshell. You're looking at an image of what a successful constructed fire bridge calculation would be. And it doesn't take long to do it all. It'll take longer to explain this presentation than it will to actually do it once you understand it. So again, the fire bridge is based on Rothermel's equations from 1972. This here is the actual tech report from 1972 from the U.S. Forest Service, and Rothermel was a research engineer stationed in the Northern Forest Fire Laboratory in Missoula, Montana, which some of my co-workers call the Smoke Lab. He was a research project leader for the Fire Physics Work Unit, and he's been retired for many years now. But how I came into possession of this was from a former co-worker at my district office that we worked out of. She was a fire ecologist taking an S490 class who had later transferred to the Cibola National Forest down in New Mexico. And she introduced me to nomograms. And I have to admit that when she did that, I at first thought to myself, you've got to be kidding me. We've known how to determine thermal intensity of a fire for 50 plus years, and nobody's put it together. So this is the origins, and we're going to get into how to put it together in a second here. But these are the origins right here. Later, in June of 1983, Rothermel produces another document, Tech Report INT-143, on how to predict the spread and intensity of forest and range fires. Now, in this report right here, I will say that Rothermel does state that one does not need to be a research scientist, an engineer, or any other type of scientist in fire behavior and prediction, etc., etc. All one needs to do is gather up the variables for the inputs, and he lists what they are, and we're going to go over that, and just plug them in where he tells you to, and then you will have the same success or reasonable rate of success as he or anybody else would at determining rates of spread and intensity. Now, keep in mind, this was developed 41 years ago, but also where I've got this underlined here, he says, and I slightly disagree with this, but he says that it would be more useful to predict fire behavior at the dispatching office before initial attack forces are sent. I would tend to disagree with that, only from the standpoint that once you understand nomograms and you have your fuels techs and your fuels leader at your district office or your state office, they can take nomograms and they can look at those troubled areas. Everybody's got a troubled spot in America. That, oh my God, we better not get a fire here. And you can take a nomogram and go, okay, let's match up the carrier fuel nomogram that most closely matches what we're looking at. And let's just throw out our historical numbers for low fuel moistures, for dead fuel moistures, and then light fuel moistures, and then the slope percent and the winds, and do several plots. You're going to come up with a rate of spread and intensity and a flame length. Once you get that number, then, as you'll see later on, you'll know what resources you need, both air and ground, or even heavy equipment. And consequently, heavy equipment for dozers and filler bunchers and massacators, fuel removal is a direct equivalent to heat absorption capacity of water. So we'll get into that more. So how does one obtain the data ahead of time? Like I said, nomograms. A nomogram is simply a device that shows the relationship between some things or certain things to find the unknown values of another object. In this case, we have three known values we use as fire inputs. Those values are the slope percent, the wind speed in miles per hour, and the fuel moisture percent. And from this, the unknown values of heat per unit area, which is in BTU per square foot, the rate of spread in chains per hour, but to be effective and useful, guys, you need to convert that to feet per second. So you just take your chains per hour, multiply it by 66, because there's 66 feet in a chain, and then get that number divided by 3,600, and that will tell you the rate of spread in feet per second. And then the BTU per second per foot and the flame lengths in feet can be determined all from this nomogram. So right now you're looking at a fuel model for Chaparral on the high wind speed side. And so up here you can see the rate of spread is about 380 chains per hour, or 7 feet per second. The heat per unit area, which is what the HPA is, that's 2,866 BTU per square foot. Now, the BTU per second per foot is 19,976. So now, when you start with this, you'll start down here in the lower left quadrant, you'll get your slope, come up to your wind speed, your measured 20-foot winds, and then you come over to the left and you get your 16-mile-an-hour winds. Once you do that, you put that over here to the right side, starting from this corner, draw a line, and you're just estimating. It doesn't have to be spot on. Even Rothermel and prior video interviews would tell you it doesn't have to be exact. Don't try to do a nice 0.05 millimeter pencil to get an exact line. That's not how this works. This is just a close estimation. And then you put the live fuel moisture, start here, and you just kind of like pencil that in all the way up. So now, keep in mind, whenever you do a nomogram, typically if you follow the Wildfire Learning Portal's Behave Plus class, they'll tell you that they like to use blue for inputs, so blue, blue, blue for dead fuel moisture, and then blue for your wind speed. Your outputs are going to be done in red. So that's why I've done the red line that you see here in red, because that's an output. But once you get this box down here is simply for determining effective wind speed, which is what this is over here. That number goes onto this side. Once you're done with that, you're done. Then you move to this, and over here you put in your live fuel moisture, if you're working with a model that's got live and dead fuel moisture. And then on the right side, you've got dead fuel moisture over here. 3% is what we're using. So you start off with 3%, okay, on your particular nomogram, okay, and you go over, you draw a line all the way across, okay. Then when you've got that, you'll slide over to where your live fuel moisture is, i.e. your moisture dampening curve is what it becomes, and then you go straight down. Now right here, I want you to know something in this area. Pay attention to that. Dead fuel moisture percent and fuel type determines your BTU per square foot. There is no other variable other than dead fuel moisture percent that controls the heat per unit area. Where the intensity comes into play is from your live fuel moisture percent and your wind speed, because this right here is just simply a turn line. So that's basically it in a nutshell, guys. Now, typically the intensity, once we get the intensity, I've always understood that to be half of an equation, the left side of the equation, if you will. And the left side of an equation is an incomplete formula because you don't know what the answer is. In other words, we can have a fire that says, oh, well, we've got 450 million BTUs per second going up. What does that really tell us? That's the whole point here. So in the upper right quadrant, the predicted fire intensity is nearly 20,000 BTU per second per foot. That's not for the entire fire line. That's only for 1 foot by 7 foot area is generating nearly 20,000 BTU every second. So what are we taught about this number and what do we do with that intensity figure? Everybody that I've talked to always says, well, they're not taught anything with the intensity figure. That's just to give you an idea of how intense the fire is, and mainly you're looking at the rate of spread and the flame lengths. That's really what they do. So with that, keep that in mind. So hence, there's no practical purpose at this point of where I'm going to determine the intensity if you don't know what to do with that intensity. But I'm going to show you what to do with that intensity, so stand by. So S390 and S490 fire behavior calculations do not cover thermodynamics at all. They do not teach heat absorption of water or retardants, and consequently, retardant guys, contrary to popular belief, cannot absorb heat because we do not drop it directly on a fire. And even if we did, according to the safety data sheets, at 194 degrees Fahrenheit, the likelihood of them generating phosphoric acid and ammonia is extremely good. So 390 and 490 again do not teach resource calculation based on thermodynamics. They do not teach how to calculate resource type or determination from intensity figures, and they do not teach basic heat exchange properties. So thermo is heat, and dynamics means a force or factor that controls or influences a process of growth, change, interaction, or activity. Again, S390 and S490 are the left side of the equation. So what does this mean? Thermodynamics is a heat force that controls or influences a process of growth, change, interaction, or activity in a wildland fire. So if we have a lot of intensity going up on a fire, and this is the thing to think about, if you have a fire that's burning and it's getting more and more intensive, more active, and more established, that heat is going to be transferred to the next adjacent fuel. That's what's called propagation. And then you have your heat generation, and then your heat flux, and then heat absorption of the fuel itself. They take into consideration specific heat capacity of the fuel and the latent heat capacity of vaporization of the moisture in the fuel to determine what the time change is going to be here. This is what the engineers do. We don't need to get into all that. All we need to do to be successful is know what the estimated carrier fuel's intensity are so that we know what to do in terms of calculating resources. So the left side equations only leave you to asking questions. For example, if the fire here, again, 450 million BTUs of intensity every second, it leaves you to, okay, so dozer line width, what size is that? Capacity of resource and operations capacity, air capacity and type, filler bunchers type and number, engine type and number. You don't know. As you can see here, our bridge is broken. So because we're typically taught this, but not what to do with it over here, we can't construct the bridge. Hence, we mismatch resources all the time on every fire that we attend. So for the past 52 years, our fire equation has stopped at the left side of the equal sign, i.e. the intensity, with no direction on how to use the number, what resource to obtain, what resource quantity or type. The active fire is the left side of the equation. The operation side is the right side of the equation. So in other words, how many resources and what type is determined by the intensity, and there's a medium in between there, and that equal sign is basically the thermal capacity of water, which we're going to get to. So the equal sign for our purposes separates the questions from the answers. So, are you only left with questions? Something to think about. Think about what you're taught and how you're taught it. So what tools can best answer these questions? Back to fire nomograms. The nomogram shown is one of the 13 original models. The nomograms use a set of input values, again, to determine a set of unknown output values for predicting a fire's rate of spread, intensity in BTU, flame lengths, etc., etc. Excuse me. If you're around folks that firmly believe that they don't need to know about temperature or BTU, or they say that they don't have time to calculate something, think about the amount of real estate that has been burnt up, or towns or structures lost because people refuse to do 5 minutes of determination from a nomogram to a simple division problem, and lost a town or structures because they mismatch resources by following standard fire run cards. Nomograms will allow you to determine cooling capacity and resource required after your intensity is determined first. Behave Plus software and nomograms alone will not tell you the resources. You have to understand properties of water and BTU to be able to do that. So you must know and understand the thermodynamic properties. So later on, if I'm teaching this to you in person, then we'll do an actual in-classroom exercise on how to do a nomogram, as well as a thermal capacity of water worksheet. So for an actual use scenario, we'll use a mock-up here. So this is kind of moving, but the chaparral is typically what you find in the California, Sierra Nevada mountain ranges in Southern California, okay? But after one selects the right nomogram for what they determine is carrying the fire, we then have to take the initial site input variables, and these are the slope percent, so we'll say it's 60% here, as you can see in the lower left corner. The wind speed, 15 miles an hour, translates to 16 miles an hour. So if we start down here, at 15 or at 60 and come up to the 15 miles an hour mark, and then go over, we're going to have approximately 16 miles an hour. So that's what that means. Live fuel moisture percent, okay, if both live and dead fuel exists, so we'll use live at 125, and you just estimate where that number is. It doesn't have to be 100% exact, guys. And then dead fuel moisture, we're going to show all the way up here in the upper right corner as 3%, and then those are your inputs. They're all in blue, and then now we're going to construct this in red, which is the red line that you see. And so we're going to have an output of about 2,866 BTU per square foot. And then what we're going to do is have a rate of spread of about 380 chains per hour, which is about right there. And then the intensity is 19,976. So this green circle right here is where the intensity is. This line has to intersect down here. It has to tie back in. If it ends up above where you started, then yeah, you did something wrong. The flame lengths are approximately 45 feet, and that is shown. If you take this intensity and kind of follow it all the way up, you can see it's up there at about 45%. So this is the point where thermodynamics and understanding such are of vital importance for one to have a greater chance of success in the wildland fire environment. So, cooling capacity of water. Let's talk about cooling capacity of water. Heat absorption, whenever you hear heat absorption, think of cooling. Because in thermodynamics, heat always goes from hot to cold. It never goes from cold to hot unless you apply heat to it. So think of a pot of water on a stove. You want to boil it for making something. You have to apply either electricity to the bottom of that through a heating element, or propane or natural gas to heat that up. And depending on your altitude and your starting temperature of the water determines how long that burner is going to have to stay on. Okay? Thermodynamics. You're putting heat and it's being transferred into the cold. The water is absorbing the heat. And consider how long it sits there before it actually boils. So heat absorption capacity actually changes with both altitude and water temperature that you're using. Thermal capacity is comprised of both specific and latent heat. Specific heat is the amount of energy that must be added to a unit of mass, i.e. a pound of water, to cause an increase of that unit, or i.e. pound, a rise in temperature. This is expressed as the amount of energy required to raise 1 pound of a substance 1 degree Fahrenheit, hence a specific amount, because unless you raise it a specific amount, it's not going to rise or fall the degrees Fahrenheit necessary. Latent heat, on the other hand, is the amount of energy required to convert a substance into a changed state. In other words, we're going from a liquid and then we're going to turn it into steam. That's a changed state, or a phase change, okay? But when you do that, you can absorb an additional 970.3 BTU per pound without an increase in temperature. And so for 5,000 feet mean sea level, 50 degrees Fahrenheit water temperature, I took the median here, it will absorb 1,123 BTU per pound. Now, if you take the BTU per pound, 1123, and multiply it by the pounds in a gallon, 8.3, you get the thermal capacity of a gallon of water, which is 9,365. The thermal capacity at sea level of water per pound is 1,132, and at 8,000 feet, it's 1,117. So 1123 for 5,000, kind of like right in the middle just about, is a really good number to use. You're not going to be off by maybe 100,000 BTU or 200,000 BTU on either side of the aisle. And then using 5,000 feet, 50 degree figure is a solid baseline to use with good thermal accuracy. So now the thermal capacity of water worksheet, again, we're not going to do this now. There's no way to do it on this presentation unless I'm doing an in-person study or instruction with you, I'm sorry. Because it's really designed to show you the steps, and you can use it for calculating gallons per minute or loads of aircraft, helicopter buckets, seats, anything like that, and even nozzles on apparatus. But it's designed to show the steps in the process one uses to determine the thermal capacity of a gallon of water or flow rate cooling capacity. And so this visually shows the steps to calculate specific and latent heat, so that way you don't get tripped up and you don't miss a step. That's really all this is. And so now we come back full circle to the FireBridge visualization, okay? And again, this is just visualize a bridge, is that mathematical construct that bridges 2 points, okay, that are related to one another but can't reach the other side to be effective until you know how to work the intensity figures. So again, if we have our 450 million BTU per second of intensity, and if we were to divide that by 1123, we would come up with 48,051 gallons need to be delivered every second. Well, a lot of people might think, well, 48,000 gallons a second, that's impossible. Well, no, you can prioritize how you want to drop this. You're still going to be there for a while. It's not going to go out instantaneously, but you're going to be more successful doing it this way than if you follow the standard move. So let's say on the other thing, like down here, if you do this with a 4,000 gallon capacity aircraft, you need 12 aircraft, or remove 16 cords of pinion if you're in that fuel type. So as an example, if you have 1 cord of pinion is 27,100,000 BTU per cord, or you can use 6 aircraft and remove 8 cords of fuel work. So you can break this up however it is conducive for your resource availability as well. But know that BTU in fuel is a direct equivalent to cooling by water. So dividing fire intensity by thermal capacity states the cooling quantity required. Now, once you know that, it's up to you to figure out how to deliver it. So fire line intensity divided by thermal capacity equals the cooling required. So if you the gallons is determined by the intensity from the nomogram times the fire line length in feet divided by the thermal capacity in BTU per gallon. And you can see down here that this is how I've worked it out for a fuel model 2 timber with grass and understory, A dead fuel is 4%. The winds are at 4 miles an hour. And this, according to the nomogram, produces a rate of spread of approximately 19 chains per hour. A heat per unit area of 500 BTU per square foot and an intensity of 174 BTU per second per foot is generated. So the rate of spread is actually 0.348 feet per second, and if you take that 0.348 multiplied by 12, you get 4.2 inches. So basically the width of the palm of your hand, or thereabout, every second is what's being burning on the ground. So substitute the values for the equation above, and the required cooling capacity becomes known. So say for your fire line is a mile long. Use the figures shown above for the BTU per gallon of water for 5,000 feet. Hence, 174 BTU per second per foot times 5280 divided by 9,365 BTU per gallon equals 98 gallons per second. So 100 gallons every second is required for a mile-long fire line. That's what that's telling you. That doesn't mean that there's not going to be other fire behind it, or it may not be started. That's just saying for that rate of spread and that intensity, that's what's required. So again, intensity divided by the thermal capacity equals the gallons. So resource determination, again, basically what we just said, intensity divided by heat absorption. I know I'm going over this quite a bit here. I'm repeating myself, but it's critical that you understand this. Fire intensity divided by the heat capacity, even the thermal capacity carried in an aircraft, will determine the number of aircraft required or the number of loads. Whether you drop 5 or 6 aircraft all in a row, or you make 5 round trips, the difference is that the same amount of water is required, the time frame changes. And fire line intensity is the rate of spread times the line length. Okay, so if you have, again, back to our roughly 20,000 BTU times a 3,000 foot line is about 60 million BTU per second generated. Divide that by the thermal capacity of a gallon, and you require 6,400 gallons. But if you don't drop it correctly, it's going to be useless. Or if you're not dropping water at all. If you're dropping retardant, then none of these figures are workable unless you're dropping water. So heat exchangers. So let's think about how this applies to heat exchangers. So what's the purpose of a heat exchanger? To keep critical equipment or components from overheating, causing a catastrophic failure. And the radiator in your apparatus is a heat exchanger. Your car, anything that needs to be kept cool is a heat exchanger. Likewise, we need to size a life-size radiator for wildfires because they're overheating. From nuclear reactors to everything that needs to be kept cool, we successfully exchange heat on a daily basis with 100% success. So if you can keep nuclear reactors cool, I'm quite sure you can size the amount of cooling required for a wildland fire. And then here you're looking at aircraft data tables, and on the far right side of each image, in this table over here, you're looking at the BTU capacity of each respective aircraft for Type 1 fixed wings and then rotors, and then Type 2 and 3 aircraft, fixed wings and rotors. And these are all the BTU capacities in millions of BTUs if you're loaded with water. If it's loaded with retardant, it's 0 BTU capacity can be removed from a wildland fire. Same with your apparatus. If you're in a Type 3 or 4 or 6 apparatus, 300-gallon apparatus, Type 6, 2.8 million BTU. A Type 3, 500-gallon tank apparatus carries 4.6 million BTU. Type 2 tender, 23.4 million BTU. Your 60-gallon per minute and 20-gallon per minute nozzles, 9,365 BTU per second and 3,120 BTU per second. So keep that in mind when you're working on your next prescribed fire, which we've had several of those get away, and they're causing us grief because this process works especially well with prescribed fire. Use the same nomogram for the same fuel that you're working with, get the intensity, and then determine what you need in cooling capacity. And there should be no, to me, there's no reason why you should have an escape fire unless you're just don't have anybody there. So in summary and conclusion, you need to cool the fire to reduce intensity. or remove the appropriate amount of BTU content to remove intensity. You guys already know that. But this is a different way to think. So FireBridge allows you to determine by how much. The resource to be used must be matched to the same unit scale generating the intensity. And as an example, attacking a fire generating 47.5 million BTU per second with a 1-inch nozzle that can only absorb 186,000 BTU per minute will be your Kobayashi Maru scenario. Thank you, and have a good afternoon.